Welcome, everybody. Thank you for joining us at the Auckland Astronomical Society YouTube channel for another exciting episode of Introduction to Astronomy. So let's get underway. Sorry, guys, the date's the 4th of May. I couldn't help myself here. Happy Star Wars. May the 4th be with you. Couldn't help myself. Let's move on, guys. Okay, so tonight's talk is titled Novae, Supernovae, and Kilonovae. What's the difference? In other words, what different mechanisms are behind the scenes causing these different phenomena? The reason I've chose this topic, I think it's important because the media and books and magazines, movies, they love to have all these images, like, a big flash fireball here. Here's a supernova remnant. It's an X-ray image of the Crab Nebula. Here's a nice new bright shining star here. So these are common images that you see, but the source omits to explain actually what's going on behind it and what different mechanisms, comparing and contrasting them. So that really raises the question, how do novae and supernovae and kilonovae, terms I'm sure you've heard before, how do they differ? And are there different types of supernovae? You seem to hear about different types. So tonight we're going to explore that. And there's really two key messages I want to impart. That, novae, supernovae, and kilonovae are different beasts. They're different events. And as for types of supernovae, there are 4 main types. There are actually quite a few types, but there's 4 main key types. To achieve this, I've split the talk into 5 sections. We're going to have a chat, just an introductory chat, about some relevant background. We'll discuss novae, in particular 2 main types of novae, classical and dwarf. We'll talk about type 1a supernovae, and then we'll talk about type 2, 1b and 1c supernovae, and also hypernovae. I don't know if you've heard that one before. And then we're going to talk about kilonovae. So first of all, the introduction and the background. 3 things I'm going to talk about here: the definition of a nova, broad classification of novae, supernovae, and kilonovae. What are the key points between them? And then in the context of this topic, a little bit about the stellar corpses, what's left over of a star when it finally ends its life. So for starters, nova actually means new star. And like a lot of things in astronomy, it's got a historical term. It just came over hundreds of years. These terms just have stuck and have stayed with us. And because often in the night sky, particularly when they didn't understand what was going on, they just saw a sudden and a transient appearance of what appeared to be a new star or a small star suddenly bright up. And I thought, hey, new star, that's a nova. And the term has stuck. So that's all the word nova means. So out of all these events, I've put them here into 3 sort of broad classes here and then split them up. So first of all, classical and dwarf novae. Then the supernovae, and you can see here, we're going to make sense of this. At the moment, this probably looks like a bit crazy, but we're going to make sense of all that shortly. And then we've got the kilonovae over there. And you'll see shortly that supernovae are classified by the prominent elements that you see in the spectra. In other words, when you put your spectroscope over the telescope and look at them, what elements do you see in all the debris and matter left over from the supernova explosion? So let's move on. Just make sure that's good. So stellar corpses in the context of these. And this is just a very, very brief overview to put a lot of the terms that I'm going to be using tonight, putting them in context, in particular in context of some of the pictures that you see. So stars up to about 8 solar masses, meaning 8 times the mass of the sun. The sun's mass is called 1 solar mass. So up to 8 times the size or the mass of our sun. At the end of their life, the outer layers of the star start gently shedding off over a few thousand years, and they leave exposed a central white dwarf core, which is just an inert core of oxygen and carbon. So when you see these sort of pictures here, These are not supernova explosions. I think that's important for you to realize that these are just sort of outer layers of a star being gently blown off over a few thousands of years. And here's your little wee central core sitting right here, and that's called a white dwarf. So stars from 8 solar masses onwards, they explode into big supernovae when they end their lives. And those stars between 8 and 20 solar masses, they go supernova in a big explosion, like you see here. This is the remnant of one. And in the middle of it, the central core after the aftermath is a neutron star, which is a hot, dense, compact star that's just packed full of neutrons. This is, you'll often hear the term a supernova remnant. So the explosion takes place over a very small confined space, and all of this here is the remnant that spreads out and out and out over many thousands of years, and that's what you're looking at there. And stars that are greater than about 20 solar masses, when they go supernova, you get all this remnant and stuff absolutely heading out. But right in the middle, you don't have so much a neutron star or a white dwarf. That's when you get your black hole. So hopefully that's just given you, put things in perspective, so you see familiar images that you've probably seen before and you think, okay, I get that now, and it's all relevant to what we're going to talk about. I put this up here because it just shows you in context, once again, all these stellar corpses, where they fit in with stellar evolution or how stars evolve. Once again, it'll make a lot more sense to us as we move forward. So here's your average star, say, like our sun. When it finishes burning hydrogen in its core, it becomes a big, fat, large red giant. Its outer layers then puff off with the planetary nebula, which we saw on the last slide, and there you're left with your white dwarf, which is small. It's important. It's really, really dense and compact. That's important. And it's really, really hot. And you'll see why that's important shortly. Here's these stars greater than 8 solar masses. They turn into red supergiants in the last few stages of their lives. When they're finished, which we'll talk about why shortly, they then go supernova. They then convert into neutron stars if they're between 8 and 20 solar masses, or black holes if they're greater than 20 solar masses or thereabouts. So I hope that just that bit of background information and overview has put the whole topic in context. So let's go ahead now and talk about novae. Yep, there are 2 main types of novae, classical and dwarf. And they both occur when you get a close binary system between a white dwarf and other particular types of stars. Now, let's back up a little bit. What is a close binary? Our sun, for example, is a star that's just quietly moving around the galaxy on its own, a solo star. Most stars are actually in star systems, and a lot of them are binary systems where you get 2 stars that as they move through the galaxy, they're actually also orbiting one another, and more to the point, orbiting a central point between the 2 of them, and they're going around like that, and that's called a binary star system. A close binary star system refers to the fact that they're critically close to one another, not sort of way out here doing that. They're actually reasonably close. So one of these is always a white dwarf in the circumstances of nova that we're talking about. One's got to be a white dwarf. Now, if that white dwarf is in a close binary star system with either a red giant, a big fat red giant, or a red supergiant or a massive star, so in other words, these big type of stars, large diameter, if they're in a close binary with a white dwarf, that's when potentially you can get a nova. So let's have a look. So what happens when you get here? Here's your white dwarf. Here's your big sort of red giant or red supergiant or massive star. If they are particularly critically close to one another, what happens is a lot of the material from this, say, red giant spills on over, gets gravitationally attracted to the white dwarf. Now, it doesn't just fly straight into the white dwarf. It actually forms into what they call an accretion disk, round and round the white dwarf like this. And there's a lot of friction that going on between particles within that accretion disk. They're moving at high speed. Another little law of physics, says that anything moving on the inside of the circle is moving a lot faster than anything further out, and so on and so on. So they're all going at different velocities, creating a lot of friction. So you immediately start getting a hot accretion disk around the white dwarf. What happens then is that this material, typically with gravity, goes round and round, and as it goes round and round, it works its way in, because it's losing heat and losing energy with the friction and so on, starts moving in, and the inner layers then start getting deposited on the surface of that white dwarf star. Now, what did we say about the white dwarf star? It's small, it's really compact and dense, and it's really hot. So as all this material and particles that once originated from the red dwarf, as they deposit themselves on the white dwarf rather, they get more and more compressed. More gets layered on top of it, and they get squashed and compressed down and heat up and heat up and heat up. Whereby you actually get a dense, shallow hydrogen atmosphere, because it's, remember, the white dwarf core is just inert carbon and oxygen, but the outer layers of these gas giants is all hydrogen. So this is all mainly hydrogen. So you end up getting a very dense, shallow hydrogen atmosphere that covers the white dwarf, and it's getting hotter and hotter and hotter, till eventually it reaches a critical temperature at which hydrogen starts fusing together, forming helium, and you start getting a nuclear reaction that runs away and immediately covers the whole of the surface of that white dwarf. Wham, bam, massive explosion as the whole thin atmosphere, compressed atmosphere of hydrogen around that oxygen and carbon core gets hot, ignites, and just goes poof. Very, very bright, and that's called a nova, or a classic nova. And here's an image from the Hubble telescope. You can see it's getting hot here, and you can just, these images were taken pre-optics repair on the Hubble, so they look a bit blurry, but here is your white dwarf here. Your classic nova explosion has occurred, and you can see this outer layer, which was once a hydrogen layer, very thin and compressed on the white dwarf, is starting to spread out with the explosion. And that gives rise to what they call a classic nova. A key point here is the white dwarf survives the explosion on its surface. So the process is set up to repeat itself over and over again. And it occurs usually every few, sort of 10,000 years or so. We'll actually come to that. So you can see here, here's your big red giant. The hydrogen has all been sucked off with gravity because they're sort of critical closeness to one another, forms the accretion disk, heats up, hydrogen fusion occurs all on the surface, whammo. And it just, the white dwarf survives, and it just keeps repeating itself. So few frequently asked questions. Yeah, how bright do these novas typically get? How long do they glow for? And how often do they occur? So let's find out. So this is called a light curve. You'll see these a lot in astronomy. It's where someone has just determined how bright something is, or its luminosity or magnitude, call it what you like. And then they do repeated measurements over a period of time and plot them on a graph here. So here's brightness. You can see it peaks at about day 6 typically. And the typical luminosity or brightness compared with our sun is 100,000 solar luminosities. And in other words, they get is typically as bright as about 100,000 times the brightness of our sun. You think, wow, you ain't seen nothing yet. Wait till you get to 1A supernovae. So, but that's bright in itself. So it peaks at about day 6 and typically fades over about 4 to 6 weeks. So you see this big, massive, bright blast go, then it fades away. And that's called a classical nova, and that will eventually repeat itself. Here is a nice little chart that that shows here. This is one that repeats itself often. You can see it going up here, comes back down, and so on and so on. Now, how often does it occur? It does depend on a few factors. For example, a bigger red giant and a bigger mass white dwarf is going to feed that transfer rate of material a lot quicker. So that's going to be more frequent. The amount of compression that goes on, which relates to the mass of the white dwarf, the more compression, the quickly it's going to ignite, and you're going to get a more frequent reaction. So it depends on the size of the white dwarf or the mass, I should say, rather, and the size of the red giant. So how about this? So that's a classical novae, where you get a big explosion on the surface of a white dwarf, and the white dwarf survives it. So what's a dwarf novae? You've got your same thing here. You've got your big red giant, large red giant, full of outer sort of layers of helium. You've got your hot, dense, compact white dwarf star sitting here. You've got your gas going across, forming this hot accretion disk, and it starts feeding in here. But something else can happen at the same time. You get a little bit of a lump of material. It can be anywhere on the disk, and it becomes what they call gravitational unstable. Instead of following the normal path and spiraling in, a big clump might sort of lift itself up. It just heads straight inwards. Either it can just land to another spot in the inner disk, or it can actually land itself directly on the surface of the white dwarf. When that happens, a thing called gravitational energy, the energy that's caught up in something because there's a gravitational force driving it somewhere, that gravitational energy suddenly gets released. And if you suddenly get a blast of release of gravitational energy, that gets released as high energy light, electromagnetic radiation. And that can be in X-rays, ultraviolets, optical wavelengths, and infrared, depending on the amount of release. And that's a sudden, violent, sharp release of light when that process happens. Now I've got some, here it is here. So here's your little hot spot coming on. You get a bit of gravitational instability, and that just jumps straight through here, either onto the white dwarf or to an inner layer. And that can occur every few days. It can occur every few weeks, every few months, every few years. It's very, very variable. It's a bit of a sort of a random event, if you will. It can be hard to predict in a lot of these systems, but you get the point. Is it's quite the timescales can be quite variable. Okay, so let's just summarizing now of classical and dwarf novae. Both, it's when you get a white dwarf in close contact with a red giant binary companion, get spillover off the outer hydrogen layer from the red giant to form the accretion disk, and it's as that disk heats up and material falls onto the surface and then gets hot until you get hydrogen fusion, that gives rise to a classical nova. Or if you get an unstable clump of disk material that suddenly decides it's going to fall inwards, then you get a sudden release of gravitational energy, and that causes your dwarf novae. So that explains what's going on with the novae and the difference between a classical and a dwarf novae. The key to it is they both involve a white dwarf and a red giant in a close binary system and a subsequent accretion disk. So let's move on from novae to supernovae. And I really split this into two groups, the type 1a supernovae and type 1b, 1c, and 2 supernovae. And you might think, really? That's a bit sort of weird looking, but yep, there's method to all of this. So let's carry on. So this is our basic chart that we had last time. Here's your classical dwarf novae here, and here's your supernovae. The bottom line is supernovae are classified by what prominence are in their spectra, what elements you can see. And it's split into two here, as you can see. If there's hydrogen in the spectra, that's immediately called a type 2 supernovae. If there's no hydrogen in the spectra, it's usually what's called a type 1. They then split it further. If you can see silicon in the spectra, you call it a type 1a. If you can't see silicon, but you can see helium, they call it a 1b. If there's no silicon, or no hydrogen, no silicon, no helium, it's called a type 1c. Now, the reason that they've sort of got this funny, looks a bit weird, once again, it's historical reasons rule. Long before they understood what was going on in these processes, all they really knew is separate something to whether you could see hydrogen in the spectra or whether you couldn't see hydrogen. Slowly over the years, they've got a better understanding of things, and they've just kept the system going. There's a good reason why you pull these apart like this, which we'll go over right now. So let's talk about the 1a supernovae. So this is another scenario when you've got that close binary system between a white dwarf and another star. The star can be a red giant, super red giant, massive star, or even another white dwarf. What happens here is white dwarfs are reasonably happy, stable objects up to a certain mass. And that critical mass is 1.4 solar masses. In other words, 1.4 times the mass of our sun. Up till then, it's stable. You start getting a white dwarf that starts accumulating material, and its mass gets above that 1.4 solar masses, becomes very unstable, and the bottom line is it explodes, which we'll come to. You might say, well, how does that happen? One of two ways. One is like your Novae scenario that we went over, how you get that siphoning of material, which you can see here, forms the accretion disk and gets layered onto it. Now, every time that thing goes nova, material, well, as it accumulates, material accumulates. Every time it gets nova, it gets material off. But slowly over time, material can quietly build up, and you can reach that critical mass. The other way it can reach that critical mass is if it merges with another white dwarf, in which case you've got a very sudden scenario of that critical mass being reached. So here we go. So there's two ways it can do it. And the explosion is very, very bright, and it's called a 1A supernova. So when you see that, essentially what's happening is a white dwarf has reached its critical mass, suddenly become unstable, and it just ends its entire life in a massive explosion. And the key here is, remember, Novae, it's only on the explosion is only on the surface of the white dwarf. The white dwarf survives to live another day and repeat the process. These scenarios, the entire white dwarf just gets catastrophically blown to pieces. So it's a one-off explosion. It occurs at 1 point solar mass. Now, the interesting thing is, because that it occurs at a set solar mass, they know the physics behind it, and it is a consistent luminosity. In other words, it's a set or a standard level of brightness. You don't get 1A supernova, sort of, one this bright and another one this bright. They all occur when a white dwarf reaches that critical mass. It goes boom into a big explosion. So it's the same consistent luminosity across the board of all these exploding white dwarfs, or type 1A supernovae. And it is because of this, they use them as what they call standard candles for measuring cosmological distances, or distances to faraway galaxies. You might say, how do they do that? Well, it comes down to the principle, if you see a bright light, and you can measure how bright it looks like from where you are, and you actually know how bright it really, really is, because you know that it was a white dwarf, 1.4 solar masses. You know how bright it looks here, you know how bright it really is, you can very quickly and easily estimate the distance between the two. So type 1A supernova are very important because they're so bright. They're actually the brightest of all the supernovae, as you'll see shortly, but you can use them as a tool to estimate distances to very, very distant galaxies. Here we go. Here's one of these light curves again. Remember, we talked about the novae, classical novae that got as bright as 100,000 solar brightnesses. Well, check out this, 10 billion times as bright. These things, when they go boof, their brightness, the absolute brightness, in other words, what they're actually doing out there in space, is 10 billion times as bright as our sun. And that's why they can see them at such long distances. And you'll see here from the slide, this particular, they tend to die off again. You'll see them, they're dropping away here. You're talking 3 or 4 months out here. So they hang around for some time. So why this particular unique spectrum? Why are these 1As over here that they've got no hydrogen, no silicon in them? They just, rather, no hydrogen, rather, and lots of silicon. So why is that so? Just think back to that stellar evolution slide. Remember that stars up to 8 solar masses, in the latter part of their lives, they just gently blow off all these outer layers to leave that exposed core. And that's what a white dwarf is. It's just an exposed, hot, inert core of carbon and oxygen. It was once at the core of that particular star. So the hydrogen and helium, there's no hydrogen and helium. When that white dwarf goes bang and explodes, there was no hydrogen and helium. That's all been sitting out here, all been blown out long ago. So there's no hydrogen and helium in there. So you certainly don't see it in the spectra. And where did the silicon come from? The high levels of silicon, that comes from the massive explosion of carbon and oxygen. Silicon is one of the elements that gets formed when you mix when you mix carbon and oxygen together with a high-powered explosion like this, you will get silicon. And that's why when you see a supernova, they look at it and they can see loads of silicon, they can see no hydrogen, no helium. They know that's a type 1a. They immediately know it's a white dwarf that's gone boof at 1.4 solar masses. They know how bright it should be. They measure how bright it looks from Earth, and you can work out the distance. So that's a little bit about what's going on there. So that's type 1a. How about the other group? Type 2, 1b, and 1c. This here's an image of a supernova remnant. That is Cassiopeia. This is an X. Most of these images are actually in X-ray. They're just such high energy events. And that little central one there, there's a neutron star in the middle in X-ray. That was taken by the Chandra X-ray Observatory, that image. Let's move on. So we've dealt with the 1A here. It's from a big thermonuclear reaction. Lots of silicon, no hydrogen, and no helium. So these ones here, these supernovas, you're talking all the ones in black. The reason you group these together, they've got one central cause, and that is a core collapse of a massive star greater than 8 solar masses. So what does all that mean? Well, let's explain further. Yes, I've done this slide. So where does all this sit? So you're getting a star greater than 8 solar masses that suddenly the core collapses and you start to get these supernovas, the type 2, 1b, and 1c. So I've split this into 3 ways to explain this in a nice logical reason what's going on here. And I'm going to ask the question, where does all this sit on the stellar evolution chart? We'll revisit that. Why do these massive stars explode into big supernovae? And why the crazy looking classification of them? So we're going to address these 3 issues, which I hope will then slowly get you to realize what's going on and why they are classified as they are. So here's our chart that we had. Remember, these were the normal stars or average stars up to 8 solar masses ending in a white dwarf. Okay, so here's your big massive star, greater than 8 solar masses, becomes a red supergiant, goes boof here into a big supernova explosion, neutron star, and a black hole in the middle. That's where we sit. Seen that one there. It's cool. So why do massive stars go supernova? Well, the bottom line is nuclear fusion in their cores stops suddenly. Just a little bit of sort of astrophysics and stuff. Stars get propped up because they spend most of their lives, they've got a huge force of gravity trying to drive them down. It compresses the core, gets hot enough for fusion, initially hydrogen into helium, but then heavier elements, and that generates energy, and that energy in that core is pushing out, and that keeps the star in check and balance, what they call hydrostatic equilibrium, where the pressure from the nuclear fusion in the core is exactly the same as the gravity pushing inwards, and you get a nice stable star. What happens is in these big massive stars, they've got so much mass and so much gravity that creates so much force, they keep burning more and more and more to heavier and heavier elements. And as they work through their way through, they can burn oxygen, then neon, then carbon, and so on and so on. They keep burning heavier and heavier elements. And in doing so, you release more and more heat, which keeps the star more and more propped up, until you reach iron at nickel in your core. And that core suddenly, instead of the core being propped open with nuclear fusions, because the nuclear fusion up to that point generates energy, you try and fuse iron together with nickel or itself, you suddenly get, you need energy put into the system, you don't get energy out. So that core that's suddenly being propped up, that core instantly collapses. What happens then is all the rest of the material and the rest of the star just suddenly just rushes inward as gravity gets the better of the situation. It just rushes inward, the stars implode, and bang, they come right up against that solid, highly compressed core, and whammo, just instantly rebound off it. So this is all happening in fractions of a second. You get the stars just collapsing into itself, hits the rigid compact core and just rebounds out again. There's a lot of material moving at high velocity, just essentially smashing into each other. Now, just going through here. So here it is here. It's those forces that cause the big explosive supernova. It's the material going in, rebounding, exploding out with extreme forces. And that results in a large explosion, but it also results in new materials, new elements being formed, which is it's a subject of another talk. So what is the reason behind them? You think, okay, I now know why massive stars go supernova. It's because they reach iron in their core, it becomes inert, no longer can you get nuclear fusion generating power. The whole system just completely collapses and then rebounds back out onto itself. You can see why. But why this crazy classification? Well, to answer this, what we need to do is have a look at some of these massive stars and what happens to their outer layers as they become more massive and larger in size. The key here is that more massive stars are less capable of retaining their outer envelopes of light elements, such as hydrogen and helium, because of two reasons. One is, as something gets larger, you're getting further and further away from the center, which means your gravitational attraction is getting less and less the further you get out. So, in other words, the gravitational attraction on the surface of a small star is a lot stronger than on the surface of a larger star. Just happens to be the way it is because you're further away from the center. So it makes sense that a star that gets larger and larger has less capable of hanging on to light elements further out. And a larger, more massive star has stronger stellar winds, with the sort of high-powered energy pouring out of it. So you can see why these stars start losing control as they get bigger of their outer atmospheres. Now, I've put here just done some simple diagrams of a star, say 8 to 40 solar masses. The star is reasonably stable. It does manage to retain its outer envelope of hydrogen and with helium just in the inside of that. So if that goes supernova, if you're watching that star and you're looking at the supernova explosion, you're going to see hydrogen, lots of hydrogen in its spectra, because that star is being able to hang on to its hydrogen. You get a star, let's say from about 40 up to 60, and I put approximately here because there's no real set levels, but I'm just probably using this as an illustration. You're starting to get quite strong stellar winds. The surface gravity is getting less and less because the star is getting fatter and fatter and it's getting further away from the center where the gravity is most strongest. So it's starting to blow off its outer layers of hydrogen, which then exposes its layer of helium underneath it. So if this star goes supernova and you're watching it, your spectrum is going to show no hydrogen because the hydrogen's long been blown off before the star collapsed, but you're starting to see its next layer of helium. So you're seeing helium in the spectra. If you get a star even more massive again, for example, just for argument's sake, more than 60 solar masses, that star has lost control of not only its hydrogen outer envelope that it's shed, but also the helium envelope is also being shed. So when that goes supernova and you're looking at it, you're seeing no hydrogen, no helium, and also you're not getting the silicon. So you're seeing where that fits on the graph then. Let's just go back to here we go. So you're seeing no hydrogen because the outer layer is being blown off, no silicon because that only comes from the white dwarf, the oxygen and the carbon, and you're seeing helium in a medium-sized massive star, and the really, really big stars, you don't even see the helium and no silicon. So you can see where that's all coming from. That's all caused by the core collapse of a massive star. Okay, and I've thrown in a term here called hypernovae. Whoa, new term. Okay, guys, so what hypernovae is, because I mentioned that because you will probably see that word getting thrown around. You think, well, what's a hypernovae? A hypernovae refers to even a really, really, really big massive star that when it goes supernova, it has the features of type 1c because there's no hydrogen in it, there's no helium in it, there's no silicon in it, so it's a type 1c. But it's so big and the energy is just funneled out. Instead of it exploding out in all directions, like sort of globally, it tends to go out in two bipolar jets where all the energy and material tends to get focused and comes out through here. And you may have heard of gamma ray bursts. Long duration gamma ray bursts are those that last for more than 2 seconds. And indeed, you get long duration gamma ray bursts come from these hypernovae, really, really massive stars that have gone supernovae. So I use that term in there. It's just sort of, it's a type 1c supernovae, and it just so happens to spread all the energy and the material out in bipolar jets. Now, here's some example of some spectra. In other words, if you're seeing a supernova and you're having a look at it with your spectroscope on, and what do you see? So first of all, is there hydrogen? And you go, yes, there's hydrogen in the spectra, and you can see here there's plenty of hydrogen here, the gamma, beta, and alpha hydrogen lines. So you immediately know that's a type 2 supernova. So you know, for example, that is from a core collapse of a massive star between about 8 and, say, 40 solar masses. If you have a look at these others, you think, well, there's no hydrogen in here. Oh, but look, there's helium in this one here, so it must be a 1b. And that tells you that a massive star has had a core collapse. It's shed its hydrogen off, so it must be, but it's got helium outer layer still there. So it must be sort of between, say, for example, say 40 and 60 solar masses. You look at this one further up here, the 1c, you don't see hydrogen, you don't see helium, you see a little bit of silicon, but not too much at all. And you know that's a type 1c, and that tells you that's a really, really big, massive star, sort of say 60, 80 solar masses, that its core has reached iron, the core suddenly collapsed in itself, you've had that imploding effect, hits the rebounds off that sort of solid, compact core, and is rebounding back out and causing an explosion. So it tells you, you just look at it, the contents of the elements that are in explosion, and it can tell you the process that's going on there, and you know how to classify them. Now this one here, they looked at it, they found no hydrogen, they found no helium, but they found heaps and heaps of silicon in there. And they immediately knew, hey, that's a type 1a, which means this is not a massive star. This is a smaller star that shed its outer layers to form a planetary nebula and a white dwarf. That white dwarf has been in a close binary relationship with another star, and it's accumulated enough material whereby it's got more massive than 1.4 solar masses, and it's become unstable and exploded itself. So that's what the spectrum looked like. That's the information they can get from them, and that's why they classify them those ways. Here's a look at some light curves. This looks a bit messy, doesn't it? But all your different color codes up here, the different types. And I suppose the main things to take away from this slide is, hey, look at all these different types of supernova. Look at the type 1a is the brightest. Remember, that was about 10 billion times the brightness or luminosity of our sun. They are the ones that they use to measure distances from faraway galaxies. And of course, they're a standard candle, because you know the mechanism that's occurring in there. It's a standard size, 1.4 solar masses. But you can see, look at that. So that's the main thing. And the other thing to take away from this graph is they all typically have slightly different peaks and slightly different fall-off rates, depending what size. And that's another way with the spectrum, they could get a grip on what sort of elements and what type of supernova that was, and hence what they call a progenitor star. In other words, what was the object there before it went supernova? It's called the progenitor star. And you can tell that by putting your spectroscope on and doing some light curves, measuring the different elements that are visible there, and plot your luminosity or brightness over a passage of days and weeks and months. Now, supernovae are important, as I hinted at before. Massive explosive forces involved, and when this happens, you're getting particles just rammed together, and that creates a lot of the heavy elements beyond iron that gets scattered throughout the universe. And the supernova does two things. One is the explosive force brings together elements to forge and create heavy elements, and that's another whole talk which we'll be doing next month. I'm going to do stellar corpses. In other words, all those corpses. If you don't get some of it, don't worry, we're going to have a whole talk just on those. And then we're going to talk about nuclear synthesis, which will go into more depth of what actually is going on in the midst of these explosions and how these heavy elements formed. But needless to say, all the elements beyond iron, because you can't create anything beyond that, because it takes energy in the core, and that's why the core collapses. But all the elements heavier than that are formed in these sort of massive type explosions. And the second purpose, of course, of a supernova is it distributes the forces, generates these heavy elements, but then spills them out across the galaxy. So it has two purposes: generates these heavy elements and disperses them. Now, that leads us on to Kilonovae. Once again, you've got a compact binary system, but this time you've got merging of either two neutron stars going around one another that eventually merge, or a neutron star and a black hole in a close binary system going around each other and eventually merging. And you get a Kilonovae in one of these scenarios. So let's explore a little bit more. So what happens, a neutron star is, as we've alluded to, is very dense, small, hot, and compact. And as the name implies, it's full of neutrons. And you suddenly get these two neutron stars that are going round and round and round, so they lose energy and they smash into each other and merge. There's a huge release of energy. In one word, it's a messy situation. But suddenly, you've got all this environment, explosive environment, high forces, and it's just rich in neutrons, because that's what neutron stars are. They're just neutrons, just packed together, and you get two of them. And you've got this real rich environment, explosive environment, rich with neutrons. What are those neutrons going to do? They're just going to get rammed together. And what does that do? It's called the R process, which, yeah, in a couple of months' time, we'll talk about S process, R process, and so on, of a condition called neutron capture, whereby the neutrons just start capturing one another and building up, building up, building up. And suddenly you get these real large nuclei, and suddenly these large nuclei then become unstable, radioactive, and they start falling to bits. And what do? They release high amounts of energy, in particular light, when they do this. So there they are, that's the merging. The neutrons are all getting captured together and called the rapid or R process, getting these huge amounts of unstable large nuclei, and you start getting gamma ray bursts. And that's where short gamma ray bursts, less than 2 seconds, comes from. You get a short burst of gamma ray. That's the most highest energy form of light you can have. But also you get ultraviolet, optical, right down to an infrared glow, and that can last for about 10 days. To give you an idea how bright they are, it's actually, the name gives that away. The brightness is roughly 1,000 times that of a classical nova, and hence the name, Kilonova, because it's 1,000 times, or kilo times, the classical nova brightness, which equates to about 1/10 and 1/100th of the brightness of a supernova. So they're nowhere near as bright as a supernova, but 1,000 times brighter than your classical nova, and hence the name, Kilonova. Their light curves are very diverse, and usually what they do is you've probably heard in the news the last 5 years or so, they've been able to detect gravitational waves and sort of analyze the mass of these objects, black holes and neutron stars, as they go around another way to eventually merge. They combine that information with the spectra and the light curve information they get by observing these events, and they combine it, and they're able to get a lot of information about the two objects that were merging, how high they were, how massive they were, how quickly they were moving, and the end product. Was it a black hole or a neutron star? This here is a Hubble Space Telescope in infrared and optical wavelengths. This was the first kilonova observation by the Hubble. So that was it there, and that was in August 2017. Kilonova, oh, spot the typo there anyway, kilonova are important sources also of heavy elements, because you're probably looking in here, and here's your exploding massive stars in green and the exploding white dwarfs. You're saying, well, hang on a minute, there's a lot of other colors down here. Merging neutron stars, as I mentioned, you're getting a lot of neutrons just ramming together, building up high, real heavy nuclei. And for that reason, the neutron star mergers has now come out as being probably the most important way that these really heavy ions, these really heavy atoms down on this part of the periodic table are formed. Once again, that's a whole separate talk, but that's one of the key importance of these neutron star mergers and Kilonovae. So tonight you've seen how Novae just means new star. It's a historical term which you frequently get in astronomy. Classical and dwarf novae, the two types of novae, and they're formed by a white dwarf in a close binary system with another star, typically a red giant or red supergiant. You get the explosion, you get the accretion disk, you get an explosion, and that tends to reoccur. Both classical and dwarf novae reoccur. The white dwarf remains intact. A type 1a supernova is, once again, you get a white dwarf in a close binary system. That's when the mass reaches that critical level of 1 point solar masses, goes boof, the whole star gets blown apart. It's catastrophic, so it's a singular event. Only happens once, and that's the end of that white dwarf. The type 2, 1b and 1c supernovae, it's due to you get a massive star, more than 8 solar masses. It forges elements right up to iron in its core. Any further fusion suddenly requires energy rather than generates energy, so the core quickly collapses. Instantly, you get a sudden inrush or imploding of the star. The material hits that solid, compact, inert core, rebounds back out again. A lot of forces are going on, and you get production of a lot of heavy elements from that. The whole star gets blown apart. It's a singular event. The kilonova is a merging of 2 neutron stars or a neutron star and a black hole that both are in a binary system. And once again, that's a singular event. That's the end of those 2 objects. That's a very messy affair. So what are you going to tell your friends when you come away from this tonight? And they say, well, what did you learn? You can say, look, novae and supernovae and kilonovae are different beasts. They're totally different processes that are going on. And there are 4 main types of supernova. So when you see a supernova explosion, you know there's more to it than meets the picture. There are 4 main types. Your 1A supernova from exploding small white dwarf, or a type 2, 1B and C supernova from a collapsing core of a massive star. That's if you've got any remaining friends who want to hear the rest of the story, of course. So when you have some quiet time, this is an image of supernova 1987A. In other words, it was a supernova and was quite bright in 1987, so that's fairly recent as well. So you can actually, I suggest you just a bit of homework. Google up supernova 1987A, bit of homework, to see how bright it was in the sky, and in particular of interest, what galaxy was it in? I think you'll find it was relatively close to the Milky Way. So that's just a little bit of homework for you. And in the meantime, I hope you've enjoyed Novae, Supernovae, and Kilonova, and you now know what's the difference between them. So I'd like to thank you for watching, and now we can look at any questions that have appeared in the chat room there, Steve.
Thank you very much, Chris. That was an incredibly interesting and informative talk. I've just got one question from Jonathan Park here. He says, can you get a kilonova from a collision or merger between a neutron star and a white dwarf star?
Interesting, Jonathan, really interesting. The answer is yes. Like Kilonovae, it's a very messy affair. It's quite a bright, messy affair because these 2 things are combining. Your white dwarf is immediately exploding, so you don't get quite the brightness of a 1A, but it is fairly bright, and it's messy because you've got all these neutrons that are being rammed together. And what is the outcome of it all? There's a paper about 2 years ago of a crowd of people, and they did some modeling of what would happen if you put a neutron star and a white dwarf together. And yes, the model showed, yes, it was very messy, it was fairly bright. And the closest in terms trying to match it up, what did it look the most like in terms of the spectra? A 1C supernova. And I thought about it, I thought, yeah, that probably makes sense, because you're dealing with a white dwarf and a neutron star, so 2 stellar corpses. So there's no outer layers of hydrogen or helium, so you're not going to see those. You won't get any silicon because you haven't got the sort of the 2 white dwarfs coming together, or the white dwarf rather coming together and exploding as such. It's not because you've got that neutron star in there as well, messing the picture up. So the closest they could put to it was no hydrogen, no helium, possibly a little bit of silicon, but not large amounts. The closest would be a 1C supernovae in terms of the spectrum. That's fairly bright, but not quite as bright as your full genuine supernova. But yeah, like a general kilonova, a very messy affair. So I hope that answers that question.
Thanks for that, Chris. We have another question here from Beechlands Observatory. When Betelgeuse, which is 11 to 19 solar masses, goes supernova, will a gravitational wave occur?
Good question. So that's different. I'm using by first principles here that my understanding is your gravitational waves mainly get detected when you're in a binary system going round one another, two quite dense, compact objects going round and round, and that as they lose energy, as they come closer and closer towards one another, they dissipate that energy in the form of ripples in the fabric of space-time, which is your gravitational waves. Now, when Betelgeuse, of course, is not in that scenario, but yes, it's going to make one big shock. So I would have, maybe there's some gravitational waves there. You might have to ask probably a gravitational wave expert, but I don't think you'd see the type of waves or the degree of waves that you certainly see from two compact objects spinning faster and faster close together and then suddenly merging. But certainly I don't doubt for a minute you get a disruption in the fabric of space-time, but whether and how you see that with our gravitational wave detectors on Earth, look, honestly, I don't know.
Thanks for that. One more question here from Rex Collins. What is the distance between the white dwarf and the red giant? I'm assuming he's talking about a 1A supernova there.
Yeah, good question, Rex. Yeah, it varies. I couldn't give you exact figures, but it varies. It depends on the size of the white, or rather the mass of the white dwarf, and also it depends on the size of the red giant or the red supergiant. Of course, the bigger they are, the further they can be apart. And it comes down, Rex, have a look up Roche lobes and particular points within the Roche lobe. So that will tell you, once it's one of those questions I couldn't give you because there's probably lots of answers to it, depending, but those big red supergiants, to give you an idea, Rex, the size of those stars, if you put one in the middle of our solar system, its surface would be out near the orbit of Jupiter, to give you the massive size of those things. So you're talking the size would probably between that and the white dwarf would be a few astronomical units. But of course, the bigger that red giant is, and also the more massive that white dwarf star is, and i.e. more gravitational attraction, the lesser that distance would have to be. So it's one of those questions, it's a variable one. So have a look up on the internet about the Roche lobes with sort of perhaps white dwarf binary systems and Roche lobes, and that will give you probably a more direct answer for what you're after there, Rex.
I think that's the end of the questions. Thank you very much, Chris. That was another interesting and informative presentation.
All right, well, thanks everyone. Stay safe, and more importantly, have fun. Cheers.